Thank you so much. Can you hear me? Okay, great. Yeah, it's my great honor to be here. Probably I'm one of the few people from academia, not industry. And yeah, this talk is about the curse of depth in large language models. Let's get started. So the outline is very simple. I will briefly introduce the background of efficient LMs for inference, and then I will tell you more about their layers in LMs are not equally trained. There are layers ineffective, and how can we leverage that for efficient LMs. Next is our main topic, the curse of depth in large language models. And I think it's already in the year 2025. I don't have to convince everyone. LMs is very expensive, powerful, but very expensive. We want to make it faster and cheaper. Because, for example, Llama 4 already has 2 billion parameters, which is impossible for people from academia or startup to run. And this is better. Okay, it is better. Okay. Yeah, and then I will briefly mention the inference bottlenecks of LLMs. First thing is we know it's massive model size. It has trillions, billions parameters, which is even hard to load the model. And it also makes it impossible to fine-tune a model without a massive amount of GPU. And another problem probably is very well-known, studied KV cache problems in context scenarios. It's probably need 30B model with 108 batch size. It requires 180 gigabytes. And reading the cache pairs from memory to cores also cause huge traffic. And another problem is the quadratic cost of self-attention. And there's ways to solve it by sparse attention, linear attention, maybe more technical innovations. And there are absolutely more bottlenecks for inference for efficient LMs. I will just talk about these 3 bottlenecks. And all these traditional compression, deep learning compression techniques can use to solve these problems, like sparsification, or another word, pruning, can be used to remove unimportant components like layers, weights, attention tokens, attention hands, or KV cache. Also, perhaps more useful techniques is quantization. You can quantize the high precedence floating point number to low precedence numbers. Even 1 bit by net is also possible. And also, you can use low rank approximation just to reduce your model size. And yeah, this is the first part. Let's go over the second part. There are ineffective layers in LMs, and how can we leverage this interesting point to accelerate our LMs. And after done many years of research in this field, my one trick pony is like here, compressing more the layers that are less effective. And you can make this, if you do pruning or if you do low rank, you can just compress these layers more to give you a higher compression ratio. Of course, there's another trick. If you have enough GPU or computing resources or data, pre-training data, you can just fine-tune your model, your prune model or compression model for sufficient time. It will also helps you to recover accuracy. But the problem here is how can we find these less effective layers, and how can we actually measure the effectiveness of layers in LMs? And I tried to answer this question with this paper, Outlier Weight Layer-Wise Sparsity. And it's a paper about LM pruning, but the technique is actually very universal. You can use it to all kinds of compression. And the notation here is input, let's assume input X and weight W with the WIG connects to the J's input to I's output. And the sparsity means the ratio of weights that are 0 in your weights, in your model. And perplexity is a well-known metric to measure the quality of your model. In architecture, I will only discuss decode only transformer. And for people who are not familiar with the pruning, what is pruning? Pruning means giving you a dense model, you can remove some unimportant components like weights or even neurals based on your criteria, loss criteria, and to trying to achieve the same performance output as your dense model. And before LLMs, there is very robust technique and simple techniques we call magnitude pruning. You can just remove the weights based on its magnitude, and it works very well on vision model. Like here is a convex model, and this is one-shot pruning without fine-tuning. You can easily remove 60% of weights without losing, with perhaps 100 accuracy drop. However, if you move to language model, this is a quite outdated OPT 175. You can only use magnitude pruning, the blue line, you can only remove 10% of weights without significant perplexity increase. And what's the reason here? So people generally believe we all know this, there's outliers in LLMs, like the output of channels is 100% or 100 times or 1K times larger than the average output channel. And if you only consider weight magnitude and you remove, for example, this top two lines in your weights probably is the based on magnitude pruning you will remove. You will likely remove also the outlier channel, which on your left height with the yellow marked. And people have shown that if you remove outliers of your language models, your model will be catastrophic destroyed. And based on this, because we know outlier is important, one simple solution, how about we consider outliers in our pruning metric or whatever compression metric? So our method is very simple. I think it's quite clear. And instead of only consider weight magnitude WIG, we multiply the output or input X GL, which is actually the input accumulation to the weights metric, IG. And this, we call it outlier score. We assign each score to every single weight. And then we calculate how many weights its outlier score is tau times larger than the average outlier score. And after calculate this, we can have this linear-wise pattern, which gives you the outlier ratio of each layer from layer 0 to layer 32 for 7B model. You can see the outlier ratio, we have more outlier weights in the starting or in the early layers than later layers. And if we consider this outlier ratio pattern, and we can rescale our sparsity, layer-wise sparsity ratio as the orange lines. So the black dashed lines is the uniform sparsity ratio. People usually apply like a Wanda or sparse GPT, like every single layer, if our sparsity ratio is 70%, every single layer has 70% sparsity ratio. But if you consider our outlier layer-wise importance, you will have this slightly tuned layer-wise ratio. And the key thing is for the layers with more outlier, we don't want to prune more. We don't want to prune it significantly. We want to preserve the outlier more. And the performance is also interesting. Like after we call it our method L, and we apply it to SODA pruning method, Wanda or sparse GPT, and at a high sparsity ratio, 70%, we can always significantly improve the pruning performance across different model. And this is quite outdated model because the paper is written 2023, so we use outdated Llama version 1, but it's a general technique that you can apply different models. And because if you sparsity is not very friendly supported by GPU, but on some other hardware like CPU developed by Deep Sparse, you can actually achieve 2.6 end-to-end speed up using their agent at sparsity 70%. If you manage to sparsify to 90%, you can get a 4 times speed up. So there's a there's a big space to develop hardware to support weight sparsity. And this outlier score, like I said, is a very universal score. No matter whatever you want to achieve, like low rank decomposition, quantization, structure pruning, parameter efficient fine-tuning, you can always consider this to improve your performance. The key takeaway here is you can just compress more of the layers with that are worse trained or yield trained, which are usually the deeper layers in all kinds of LLMs. And motivated by this, actually, as a researcher, I'm pretty happy to see this happening in almost all LLMs, because it just gives you another more paper in different compression field. However, it keeps me awake during night. I mean, you can continuously see this pattern across different models. And this is Llama model from 7B. I will present later. We also test it on more state-of-art model, Quaven or DeepSeek. It's all have this pattern. You can see across the larger model you have, the deeper layers there are more deeper layers that doesn't contribute as we expected. And another proof or interesting thing is NVIDIA maybe last year they also used this similar thing. They pruned 15 blocks or layers from their 15B model and get this miniature 8B, which versus Soda based on layer pruning. So this all evidence provides some proof like there are something ill-trained in the LLMs, which are overly overlooked by the people. And my intuition here, my goal is here, okay, it's a good indicator for us to do model compression, but does that also mean we are wasting a lot of computing resources? Have a model that should be better if we can fully utilize these resources or make these deeper layers better. And this is I call it the curse of depth in LLMs. Like deeper layers in LLMs contribute significantly less, but not nothing, to learning and representation compared to early layers. And my thought is, ideally, we want our model should be well-trained with sufficient diversity in features from layer to layer, from top to bottom, to maximize the utility of networks parameters, because we all know how costly to train our language models. And given this motivation, our next question is, what is the root cause of these ineffective layers in LLMs? Maybe I just pose this question to the audience. Any guesses why? What is the root cause of this? Why deeper layers always contribute less? Yeah, similar. Close. And my bet is here. Oh no, this is the previous layer. My bet is here. So my bet here is the layer norm actually caused the ineffective later layers here, because before this current SODA models like Transformer, BERT, or T5, they all apply what we call post-layer norm. The layer norm is, I don't know if I can point. The layer norm is applied after the addition or after the skip connection. But now all these language models, I think except for Gamma or something, they use sandwich norm. They use pre-layer norm, which we apply layer norm before sub-layer attention or FFN. And why that is the problem, I will explain later. So my hypothesis is pre-LN tends to produce smaller gradients in deep layer, because we all know layer norm is help to propagate gradients. No matter how deep you stack your layer, you can always train your model easily without heavily fine-tuning your learning rates compared to post-layer norm. So pre-layer norm tends to produce smaller gradients in deeper layers. therefore has more effective shallow layers. So shallow layers in pre-layer norm is more important. Post-layer norm, on the other hand, reduce larger gradients in the deeper layers, but also cause gradient vanishing in the shallow layers. I will prove it right away. So in order to evaluate this hypothesis, we just one method is just to compare LMs with identical settings except for the layer norm, right? So we evaluate two types of models. One is open weighted large scale weights. So at that moment we have llama 2, which is pre-layer norm, and comparison is BERT, which is post-layer norm. And because the only difference, this layer norm is not the only difference between BERT and llama, we also train our own model, small model, 130 million, where the only difference is pre-layer norm and post-layer norm. And we use three metrics, angular distance between layers, to which we believe if the layer is more similar, their features are more similar to its adjacent layers, that means they are less important. You can remove without a significant drop. Another thing is you can directly remove the layer. Like you can entirely delete the layers without fine tuning. If the performance drop is huge, that means this contributes larger in your model. And another thing, we also plot gradient norm, just to say what it goes. And yeah, this is our pre-trained model setting. We compare BERT on left with the llama on the right. You can see the top row is the angular distance across layers. So each point from bottom to top means the layer's feature, the angular distance of the current layer to its adjacent next layer, or next 5, next 10 layers. And you can see the yellow means the distance is smaller. So we can see BERT model has very similar early layers. And on the bottom is performance drop if you drop one single layer without fine tuning. You can see BERT model has you can actually easily drop some layers of the early layer without performance. This is a squad performance without performance significantly drop. And on the other hand, llama actually has very similar later layers. And you can see later layers has quite high similarity with their adjacent layers. And you can actually drop almost half of the layer. I mean, this is like one-shot drop without fine tuning. And even with fine tuning, I think you can drop more. And how about, people might ask, how about this more recent models? We also measured Mistral 7B, Quaven 7B, Llama, DeepSeek. They all have this consistent pattern. And as I said, the only difference between BERT and Llama is not the layer norm. Their dataset is also different. So we train our model with Llama 130M, and with the same, only difference is layer norm. And again, post-layer norm has very similar early layers, and pre-layer norm here, their later layers are more similar, and you can drop some layers without hurt your performance. And this is gradient norm. You can see the red color is gradient norm. No, blue color is gradient norm post LN. So post LN has quite big gradients in your back deeper layers, and post pre LN has very small gradients. And yeah, this is our empirical evaluation of our hypothesis. So like layer norm is the root cause of the deeper layers ineffectiveness. And also we do some simple math, and we can mathematically prove there's some issue in pre-layer norm. So this is the formulation of post-layer norm and pre-layer norm. If you calculate the derivative of these two, you will have this math, and they have one common thing, which is the Jacobi matrix of a layer norm to its input x. If we assume our input x follows a normal distribution with a mean of 0, and sigma x is the variance of the input, we have the Jacobi matrix of layer norm equals to equals to here equals to 1 over sigma x times identity mapping. And here we will have a problem here because for I don't know, I can point something because maybe I can point here. So for pre-layer norm, we actually don't constrain or normalize the escape connection or residual block over step the layers. But for post-layer norm, we every escape connection is normalized by layer norm. Why this is matter? Because pre-out and if you don't constrain this, will cause this the variance of input accumulated exponentially because we don't actually constrain it. As your layer accumulated, your output will be. We prove this semi-exponentially grows, but that means the sigma x prime will be very big. And this causes this part, the Jacobi matrix equals to 0. And if this is 0, which means this part will go to 0. And this will means in total overall block, the derivative of this block will equals to identity mapping. Okay, for identity mapping, the benefits is, okay, you can still train your model with identity mapping in the back propagate. Nothing, you just propagate your gradients to your previous layer, but actually it doesn't contribute meaningfully as we expected. And we also have some visualization of output variance. And you can see from bottom to top, from the first layer to the 10 layers, the variance actually grows largely as your layer goes deep as training. And this actually explains why the deeper layers contribute less than we expected. And our fix is very simple because we figured out the root cause is the variance become too big in deeper layers and it causes the gradients, the Jacobi matrix becomes to 0. So how about we scale down the variance of your output, our layer norm. So this is exactly what we did. We scaled down the output of a layer norm by the square root of depth. A very simple trick. And you can also maybe input it at initialization. And this is our method is over there. And you can see after applying our method, you can successfully constrain or scale down your variance from 175 to 25. And we used our method to do our pre-training across 130 million to 1B with the mediocre tokens. We cannot afford more. But we can consistently see the performance improvement if you scale down your variance. And we were asked to conduct, maybe can you scale up to 7B model? So we scale up 7B model with a 33 billion token. With OMO, this is OMO architecture, and we can also deliver consistent lower perplexity. We also tried to the latest architecture, Quaven 2.5, of course, small model, 0.5 billion. We also achieve consistent performance improvement. And to give you evidence why it's actually leads to more effective layers, we perform layer drop on our toy model. So you can see with layer drop, our model, like yellow color, orange color, has more useful deeper layers than pre-layer norm. And this is the visualization of angular distance across layers. And the red line is our method. We can see this is angular distance. The higher distance means there are a larger feature distance across layers. And yeah, hopefully I convince you there's some issue of pre-layer norm or current LMs. The deeper layers doesn't contribute as much as we expected, and you can. There's there's ways to fix it pre-training, but we're still figure out how to fix it post-training because not everyone can afford pre-training. Perhaps there are so many people from industry you can afford pre-training your model by train more but have more meaningful layers across depths. So the conclusion here is the curse of depth in LLMs is ubiquitous, and the pre-layer norm is your root cause. You can fix this by adjusting your output of your deeper layers. And there are some future directions I'm personally very interested. How can we further leverage the curse of depth to do model compression? I mean, model compression is always a big issue in practice. And is it possible to fix this issue post-training, in a post-training way? Because if we can do that, it just reduce many resources to pre-training again. And we also found vision transformer actually suffer less from this curse of depth. Maybe because the data is more continuous or they don't have casual attention. We don't fully understand this, but we are interested to do further research. I think that's all for my talk. Thank you.
All right, thank you, Dr. Liu. Any question for Dr. Liu? Any question? Okay, it's this lady here.